my name is Devin Dunaway.
I'm James Seals.
And I'm Jordan Mack.
And we're doing our video on elastic collision when both the momentum and kinetic energy is conserved. So in this example, I'm doing it with some billiard balls and a pool cue stick.
The cue ball has initial velocity of 3.5 meters per second, and the target ball is initially at rest with 0 meters per second. The cue ball has a mass of 9.5 kilograms, and the target ball has a mass of 10 kilograms. For the sake of this example, let's assume both objects are on a frictionless surface with a completely elastic collision.
Since the collision is elastic, we can assume that no energy is lost, meaning the total energy for the system is equal to the energy before the collision and also equal to the energy after the collision. Since the target ball is initially at rest, we can determine that the equation for the conservation of kinetic energy is 1/2 m1 v1 initial squared equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared.
From an overhead perspective, we can see that when the two balls collide with one another, they ricochet at an angle away from the horizontal. The cue ball bounces off at an angle of 60 degrees below the horizontal at a velocity of 2 meters per second. We are in charge of finding the final velocity of the target ball along with what angle above the horizontal it travels at. We can use the law of conservation of momentum to find these two components, which we will demonstrate in a PowerPoint presentation.
Elastic Collision Physics by
Devin Dunaway.
James Seals.
Jordan McLendon.
Introduction, background, and objective. The topic of this video is elastic collision. An elastic collision is defined as a collision when both the momentum and kinetic energy of the objects are conserved. Common examples of elastic collisions include atom collisions, bouncing a ball on the ground, and billiard balls, of which we are using in this example. We intend to demonstrate the law of conservation of momentum through the use of these billiard balls. Our results will show that we are able to calculate the final velocity of one ball using the momentum equation when given the final and initial velocity of the other ball in an elastic collision.
Formulas that we will be using in this project would be momentum, which is P equals mass times velocity, and conservation of momentum, m1 times v1 plus m2 times v2 equals m1 v prime 1 plus m2 v prime 2.
Since this is a two-dimensional physics problem, we must break the momentum equation into x and y components. The horizontal momentum equation Px is equal to m1 v1x plus m2 v2x equals m1 v prime 1x plus m2 v prime 2x. Since the target ball is initially at rest, we can write its initial velocity at 0, which simplifies the equation to m1 v1x equals m1 v prime 1x plus m2 v prime 2x.
Looking at the y component of the momentum equation, we know that the cue ball has no initiated velocity in the y direction, and neither does the target ball. Therefore, the initial momentum in the y direction is equal to 0, and the final y momentums of the balls are equal and opposite.
When plugging in the masses and initial velocities of both balls into the horizontal momentum equation, we arrive at the equation 33 kilogram meters per second is equal to 9.5 kilograms times the v prime 1x plus 10 kilograms times v prime 2x. Using trig, we know the horizontal component of the cue ball's final velocity is equal to 2 times the cosine of 60 degrees, or 1 meters per second. Plugging this number back into our equation allows us to solve for the final horizontal velocity of the target ball, which is approximately 2.4 meters per second.
Following similar steps for the y component of the momentum, we know that the y component of the final velocity of the cue ball is equal to -2 sine 60 because it is downwards. We also know that since both balls have no initial y velocities, the y components of their momentums are equal and opposite. This leads us to the equation v prime 2y is equal to 9.5 kilograms meters per second times the square root of 3 meters per second divided by 10 kilograms, which is approximately 1.6 meters per second.
Now that we have the x and y components of the target ball's final velocity, we can use the Pythagorean theorem to find its total final velocity. The square root of 2.4 meters per second plus 1.6 meters per second is equal to 2.9 meters per second, which is the target ball's final velocity.
To find the angle from horizontal, we simply take the arctangent of the y component divided by the x component, and we get 34 degrees.
In summary, we were given the initial and final velocity of the cue ball along with its angle from horizontal, and using the horizontal and vertical components of the conservation of momentum equation, we were able to find the horizontal and vertical components of the target ball's final velocity. Then, using Pythagorean theorem and trigonometry, we were able to determine the overall final velocity and angle of the target ball. This presentation demonstrated understanding of elastic collisions, conservation of momentum, vector quantities, and basic trigonometry.